Hi, this is the first session for PRISMS-Plasticity trainings, and I'm Reza, the lead developer of PRISMS-Plasticity at Prism Center, University of Michigan. I'm very happy to have you here. During the training, you have any questions, you can put it in the chat box, as someone has already done that. Okay, so for the PDF, I'm gonna go and explain it. So if you have an Internet Explorer, so there are two places. You have already have the PDF in your virtual machine. So I just want to show it, and then I will show you where you can find it on the internet. So the first place is if you go on the home, and then on the home, you can go to the tools. This is the place, home tools, for all the tools that we have trainings for within virtual machine. And there is a folder for plasticity. And then this is Prism's plasticity folder pretty much. So if you see here, there is a training materials. So double click on that. There will be a training 2022. And then there would be two PDFs. So the first one is the one that I'm actually showing. If you don't want to open it here and you have two monitors and you would like to open it on the next monitor, another way to do that is open the Prism's Plasticity GitHub folder. So you can say Prism's Plasticity GitHub. So doing that, the first link will comes up as Prism Center GitHub for Prism's Plasticity. And if you click on that, then you would see Prism Center Plasticity, which is Prism's Plasticity GitHub. And then there is a training materials here, and then trainings 2022. And then there are two PDFs, for example, PDF 1, and then you can download them. So this is the second way you can actually get it. And you can open it on your second Windows. It would be nice to have it as a separate in case you want to copy. And I'll switch back and forth between the virtual machine and PDF just in case. But this is the second way to get it. So now this is where you can get the PDF. So just a very brief 2 slides introduction in case you missed the elaborated Prism's plasticity talk. Excuse me. So what is crystal plastifying element in general? Crystal plastifying element in general is like any other finite element method. So like any other specifically continuum mechanics finite element method, you will discretize the body, and then you will solve the equilibrium equations to update the stress strain in each increment. In the case of crystal plastifying element, what will happen is at each integration point for each element, the crystal plasticity will solve for you the stress strain relation, or basically what typically people call constitutive model. And you will give deformation gradients or mesodeformation gradients from the FE solver. The crystal plasticity solver will solve that for you, and then pass back the mesoscale stress and consistent tangent modulus to the FE solver. So this is the general idea of how crystal plastifying element works. Why we are using Prism's plasticity? There are different features that are make this software interesting. The biggest one is it's actually very highly scalable. So if you have a very large scale crystal plastifying element simulation, as I will show you in the next slide, many of the commercial software are much limited. And on top of that, you need to pay a lot of money for the licenses. For example, if you are using Abacus with multiple number of processors, you need to pay a lot of licenses for your parallel simulation. And on top of that, it has a variety of models and it's very flexible. So it's not like in black box. You can actually start changing the code if you want to add a module. And there are a lot of good documentation about it, YouTube video tutorials, and there are trainings like this one that we have. And just to give you an idea, when I'm talking about scaling, what I'm talking about is, in this case, we model a cyclic response of polycrystalline aluminum alloy 7075 T6, which has about 7,500 grains, and it has been discretized by about 720 elements. And we use periodic boundary conditions and uniaxial cyclic loading. You can see that and we compared the scalability with Abacus. So what we end up with is, you can see the stress strain response is almost matching, but this is the scalability graph. So this is wall time, the required time to finish the simulation. And on the x-axis, you have the number of processors. So the blue data is for PRISMS-Plasticity and the red data is for Abacus. And the dotted data is the ideal scaling, which shows you if your software is ideally scaled, it means that if you double the number of processors, your simulation should be finished in half of the time. But this is not the case in reality. So in the case of Abacus, you can see after the number of processors goes more than about 100, 120, you will start to see a plateau. It means that it doesn't matter to use more processors. You will not get more efficiency out of the simulation. However, in the case of Prisms, you will still get the efficiency. You'll get still the efficiency out of the simulation, and still it's getting a little bit deviated from ideal scaling. But in the bottom line was, what we observed was, using PRISMS-Plasticity and 480 processors, you can finish that simulation in about 1 hour. However, in the case of Abacus, it required about 28 hours to finish that kind of simulation. So it gives you the idea about how the scaling is different for very large scale simulations. And that's on top of the licensing. So that's just an opening slide to why you should learn the PRISMS-Plasticity. But as I mentioned, the first part of this training would be going over all the required input files, giving you some idea about what are the input files for each crystal plastifying simulation using PRISMS-Plasticity, and then doing one simulation for today. And we are hopefully finishing about 1:45 to give you like 15 minutes break between PRISMS-Plasticity and Prisms fatigue session, which will be the follow-up session for PRISMS-Plasticity. So we start with so as I mentioned, you can actually Google the PRISMS-Plasticity GitHub, and this is the first page that you would see. There are training materials that you can go over. There are many applications that we will visit, some of them today. There are documentations which you can go and see information about different features, installation, and there are the source files and the header files and some testing and some utilities and some general information about the code itself and where you actually can share your comments or concerns about the code. So we are, as a developers, we can follow up with those questions. So this is generally pretty much what you will see in the GitHub for PRISMS-Plasticity. So what are the main files? So as you can see here, I will go over one of the application to show you the input file. So if you open your virtual machine, let's start from the scratch. So in this session, there are two ways that you can actually open or modify your input files. So the first way, which is very simple, is going directly to the text files and open them as a text editor. So for example, the first application is within tools. So if you see here, this is the first applications that we have here. Is close this one. Okay, so this is plasticity applications, crystal plasticity, FCC compression. So this is the applications that I will open. So to go to that application, you need to go to Home, Prisms, Tools, or Tools, and then open plasticity, and then the rest of the address is there. It's application, crystal plasticity, FCC, compression. And then these are the files that I will go over right now. So there are two, can you oh yeah, it would be recorded. So the session, as I mentioned before, will be recorded and will be provided in YouTube within 2 weeks. So that's fine. So these are the files. So you can directly open the files with text editor by double click on that. An alternative way, which is actually the original way, would be, let me close this so we start from the scratch, is the terminal. So within the terminal, let me zoom in a little bit. Okay, I think this is enough. So first, when you open it, it's in the home directory. So you need to go by CD tools. It will go to the tools directory. So if you see all the directory here, plasticity is one of them. So now you go to CD plasticity, and if you click on tab, it will actually auto finish the word for you. So the next one is application, crystal plasticity, FCC, compression, and it's the same folder as I just showed you before. And if you want to open any of those files, you should use like any text editor. I'm comfortable with Vim, so I just open the file like this. So that's how you would open it. Now let's go back here and let's open the PDF again. So the first set of files are prm.prm, which is the main file here. And then you would have boundary condition info, which is the boundary condition you're applying, grain ID, which is the grain ID. Latent hardening provides information for latent hardening within that material. Orientation is the grain orientation for each grain ID. Slip direction and slip normal is a crystallographic information for each slip system. I will go over each of these one by one to give you a full details of what are the specs for these files. So the first one is if you open the grain ID, let's go back here, see which one is. Oh, and this is a few commands for you if you don't have any familiarity with Linux terminal. So these are a few commands that I will use mostly today, so you can see the usage of each command for today's training. So the first file is orientations.txt. So if you open the orientations.txt, you will see a file like this. Let me open it here. So this is pretty much a file which something that it looked like. So the first line, it's a it doesn't matter, it's just an information star. It doesn't have any real information, so you can just replace it with a bunch of zeros. So the real information will start from the second line and after that. So the first column here, it's about the grain ID. So it starts from 1 all the way down to the number of grains. And each column, each 3 columns are the Rodriguez representation, Rodriguez vector space representation of that orientation. And this is the orientation we are using for our crystal plastifying element simulation for each grain ID. But besides this information, there are a few additions you might want to have. So the first one is If you want to have multi-phase simulation, you need to have another column added to this orientations, which will define the phase of each grain. So that number, it could be a grain or it could be a phase of a grain. So for example, if grain number 1 is phase 1, I will add another column at the end of here with the number 1. And if the next one is number 2, I will add another one. So it would be an additional column to this information. Another information is, let's say you have a kind of residual stress for each grain, and you want to read in that data. So any grain level input that you want to read in should be added as a feature, like we call it additional voxel info. That will come in as well as another additional column here. So let's say you want to input any user defined value for each grain ID. So it's a grain level information. Then you need to add another column here and then provide that information, and you can easily access those information within the code. So it's typically a feature for advanced users if they want to develop their own model or their own feature and want to play around with those information. So that's another feature you would have with the orientations.txt. But for defining a 3D macrostructure, now just giving the orientation for each grain ID would not be enough. You need to know the spatial representation of the grain IDs. So another file for that would be grainid.txt. So grainid.txt will be a file which is basically a 2D representation of a 3D macrostructure. So the way we do that is it has a certain format which we taken from the Dream 3D software. And in that format, if you have a representation of N1 by N2 by N3 voxels in 3D, we map it to the 2D file with N1 times N2 will be your number of rows, and number of columns would be N3. And that's kind of like here it's explained how the format will be defined. On the follow-up session tomorrow, I will actually generate some grain ID and orientations.txt using Dream 3D for you from an experimental EBSD data to show you how you would start from a set of experimental EBSD file, generate the files required for PRISMS-Plasticity simulation. If you have that kind of representation, you can actually check how this format matches with this file, and that would be your grain ID. But the information that you need to know about grainid.txt is number of header lines. By number of header lines, I mean the number of information you have before the real grain ID file starts. In this case, you have 20 lines of header. And after that, you need to have the number of voxels in each direction, which is N1, N2, and N3. Those two sets of information are required from the grain ID txt for prm.prm, which is the core of the input files. So this is the second file for the inputs. But now that I explained the macro structure, let's go over the main prm.prm. Let me open the prm.prm here. So if you go back to your folder, you can open the prm.prm for compression file here, or you can go to your terminal and just say vim prm.prm. So this is how you can open it. There are two ways to open it. So we are going to try to go line by line and give you some hints about what each line works for, or how these lines are working. So we don't have any question in the chat box, so we'll continue. So let's go back to this. So the first two lines here, order of find element order of quadrature points. So you can, so before the last version of deal 2, which PRISMS-Plasticity is built upon of that, FE solver, we could have only used the hex mesh structured and unstructured. But deal 2 is starting their previous version, start releasing the test case for TET meshes as well. We didn't incorporate that yet, but we hopefully incorporated that in our next release. But for now, the code can capture structured or unstructured hexaedral meshes. So that hex meshes or elements can have different order. It could be linear, nonlinear order 2 or 3. You can define that element order here. And then the order of quadrature points is defined here, which define what the number of quadrature points you are using for elements. So for example, for a linear element, we know that the order of quadrature points to accurately integrate the stiffness matrix or residual forces should be 2. And when you're saying the order of quadrature is 2, it means that in 3D, you will have 2 by 2 by 2, which is 8 number of quadrature points for that element. So these 2 lines defines that information. And the next lines, it's number of dimension. For PRISMS-Plasticity, it's always 3. So the code is doing 3D crystal plastifying element, and then it would be the dimension of sample within 3 within the 3 dimensions. So it's the size of a cube with a unit, with a length scale of unit. So the next lines, actually the next part is defining the mesh quality. So this part is interesting. You can refine your mesh 2 ways. The first way is subdivisions. So for example, if you would like to have 2 by 4 by 5, the easiest way is to make it subdivision along x2, subdivision along y4, and subdivision along z is 5. But there is another way to refine the mesh further, which is set refine factor here. So what this does is for each element, it will divide it. It will add a point in the center. For example, if set refine factor is 1, it refine each element to 8 elements, 8 equal elements. And if you make it 2, it goes 1 more level, and one of those, for each one of those smaller elements, it makes it 8 more elements. So for example, here, if you have 2 by 2 by 2, you have 8 elements with subdivision. And if you have set refine factor of 2, each elements will become, in each direction will become 4. So at the end, you will have 8 by 8 by 8 elements. But what's the difference between the first one and the second one? So in your small simulation, it doesn't matter much, but generally speaking, the set refine factor, it consumes less memory compared to set subdivision. But what is the underlying reason for that? The way deal 2 works is whatever mesh refinement you're using subdivision, that would be your coarse mesh. But it has, so for each processor should save all the information for all the coarse meshes. For example, if you define 100 by 100 by 100, each processor in multiple processor simulation have to record the information for all mesh geometry for that all 100 by 100 by 100. But if rather than that, you're using set refine factor, for example, let's say you're having subdivisions 1, 1, 1. It means that you have 1 coarse element. And then using set refine factor of 5. So your mesh is 32 by 32 by 32. So what happened is each processor just then save the information for the mesh for the region that it requires on the fine level, and record the information for the mesh on the course level for the entire course mesh. So then each processor only record the information for one small patch of the whole mesh. However, rather using the 1, 1, 1, and 5 here, if you would have used 32, 32, and 32 for subdivision and 0 on refine factor, then each processor have to record the information for all of the 32 by 32 by 32 mesh. So in general, it's always, if it's possible to refine anything by refine factor, it's better to do that. But there are two exceptions that you cannot use that. One of them is applying periodic boundary conditions. So if you are applying periodic boundary conditions, you cannot use set refine factor, and you always have to use set subdivision. And another one is grain ID deletion. So if there is a feature that I will cover tomorrow, and that's you can actually delete some elements based on the grain ID to generate porosity or notch. If you want to use that, you cannot use set refine factor. But besides this, you can always have your external mesh generation. So rather than asking DIL2 to generate the mesh for you, you can always have your external mesh, and which can be read in for you. And the format for that is a Gmesh format. So for example, if you generate a Gmesh format, DIL2 can read it in. PRISMS-Plasticity can model that mesh itself. So if you go to your folder here, and then go back one folder, there is a simple tension external mesh. And this specific file, it will provide the information for you for both grain ID and external mesh. So this file, as you can see that there is no grain ID.txt here. So this file will cover both external mesh and the grain IDs for each element. So that's the file you actually requires. Oh, there is one question. If periodic boundary condition, when what should be set the refine factor? So if you are using periodic boundary condition, the refine factor should be 0. And then you need to use the subdivisions to discretize the sample. For example, if you want to do 32 by 32 by 32, you need to define the subdivision X, Y, and Z 32. You cannot use this set refine factor. So in that case, set refine factor should be 0. So you can always define the external mesh. There is a parameter in the case of external mesh that you need to define, and it's very interesting. It's external mesh parameter, which is, it's tricky because when you're defining the external mesh, there are some round of error. When you are generating the mesh using DIL2, the numbers are exact. So for example, if you define a boundary condition on a node, the number would be exact. But when you're reading external mesh, let's say rather than defining x equal to 0.2, the external mesh defines the x equal to 0.1999. Then you need to have a certain threshold to define what is, when you're assigning boundary condition, what should you consider as 0.2 to apply a boundary condition. Then that threshold is defined by this external mesh parameter. And this external mesh parameter times the domain size in each direction will define that threshold. So for example, if you define a boundary of 0 to 1 for your external mesh in all X, Y, and Z, and then apply some boundary condition on X equal to 0 for all the nodes, it might happen that your external mesh doesn't generate the actual 0, but like 0.0001. Then your code needs to know what would be your threshold to consider for that? That's when you define your threshold. So that's the case of external mesh generation. Set number of dimensions should be, no, it's, yeah, the current version, it's only working for 3D simulation. So it should be always 3. If you want to model 2D, then you can model a very thin layer of 3D elements. So that would be the way to model 2D simulation. So basically you can model plane strain, but plane stress, because there are certain modifications for plane strain, that would be hard to model with the current version. Okay, so what are the next part? Output parameters. Okay. So if you go down, this is the output parameters for you. So before I explain these output parameters, let me explain some general idea about the outputs of PRISMS-Plasticity. There are 3 outputs that you can print out using PRISMS-Plasticity. One is the basic one, which is, we call it the stress strain.txt, is the average response of a certain variables like sigma in all direction, or stress 1,1, stress 2,2, and a strain, and the total plastic sleeve, total twin volume, this kind of information in average form. So it doesn't give you spatial information, it just gives you the average information, and that's good for your calibration. Because typically what you do in calibration is you have, for example, stress strain from an experiment, and that's like an average response. So if you want to calibrate your model, you need to have some sort of average output. So that stress strain.txt will be outputted no matter what you define here. So that's the best, that's the most basic output for PRISMS-Plasticity. After that, all of the other 2 outputs can be switched off or on depending the keyword you're using here. So the second type of output, which we define here, is VTU or PVTU files, which can be opened by ParaView, and it will give you the spatial visualization of results like 1 meter stress, 1 meter strain, grain ID, twin fraction, all of those information that can be opened by ParaView, and that will give you the visualization results for your response. The deformed sample, all of those information will be handled by this output. And I will show you an example today later on how you can actually visualize these results. The third type is quadrature output. So the problem with visualization is not the problem, the quality of those information is not at the grain level, at the grain quadrature point level, but they will give you a visualization results. But what if you want to do quantify those variables at each quadrature points? So then there is a certain type of output, which we call it quadrature output, which output whatever information you want for each quadrature points. So these 3 types of information can be outputted by PRISMS-Plasticity. So if you open this, we can go one by one. So for the PVTU or VTU file, if you want to print them out, you need to set the right output true. If you make it false, it won't print it out for you. And you can define the name of the folder that the output for PRISMS-Plasticity will be recorded in that folder. And the set skip output steps define for that kind of VTU or visualization results, how frequent you want to output those results. So for example, here, this says print out those every increment, which is too much, but it's just an example. Then you need to define which of these basic variables or state variables you want to actually output. So either one of those, you put the flag true, it will output it for you. And besides this information, it will output the nodal deformation for you as well. And but there is an advanced feature for this that I will cover tomorrow. And if you want to visualize a user-defined variable as a part of this, what should you do? Then I'll cover that tomorrow. If you, let's say, instead of having equivalent stress or strain, you just want to visualize sigma 1,1. What should you do? So that's the part that I will cover tomorrow. There is a capability for that. And as I mentioned, the third type of output is quadrature output. So if you want to output those information, you need to put this flag there, set right quadrature output equal to true. If you don't put it there, it means it's false. For example, here, there is no set quadrature output true. It means that it won't print it out for you. So if you want to print it out, that information, you need to set it true. And then again, how frequent you want that skip quadrature output printed for you. But the question is, what type of information at quadrature level will be outputted by quadrature output feature? So to open that, there is a link. So rather than opening the link, I will show you how you can go over it. So this is the PRISMS-Plasticity folder on GitHub. If you go on source, material models, crystal plasticity, there is a file which most of the visualization and post-processing data will be in that script. So if you open update after increment.cc, this is the file which after you converge each increment, then you need to generate all the visualization results. You need to, this script for you does most of the job. So as I mentioned in the PDF, all the quadrature outputs start, this line number might not be accurate because I keep updating the code. But this part, if you search for this line, this is what actually we have for starting the variables that's getting outputted by quadrature output. So if you Control F here, so this line, so now it's 302. So this is basically starting the variable outputting for quadrature outputs. And you can see it start with the grain ID of each quadrature point. And the interesting thing is you can comment out whatever you don't like from here, and it will be finished. If you go back here and copy this here, that would be the end line. So this would be the last line. So anything before that will be printed out as quadrature output. So you can see it has slip fraction, it has Cauchy stress, deformation gradient, plastic part, elastic part, updated rotation for each quadrature point, tween, if it's tweened or not, the Jacobian or the weight of each quadrature point, the phase if you have multi-phase, and the grain ID. So any of those you don't like to print out. So let's say what I need is just the grain ID for each quadrature point and the coordinate system of those quadrature points. And I don't need to print out anything else. What you would do is you would comment out by using these two. You would comment out all the lines that you don't want and recompile the code. So this is something you need to do once for your specific application. So for your specific application, if you want to change the default format, why you have to do that? You don't have to do that. If you don't touch anything, it will print out all of this information for you for each quadrature point. But considering if you have a large simulation, you don't actually want to print out all of this information. So what you would do is you need to comment out some of those that you don't like, and then just focus on the one that you want to print out. So, or on the other hand, if you want to add anything else, you just change this variable inside this parentheses and then print out that. So that's how you change the quadrature output, the parameters you want. But be careful, if you change this file, hopefully once, you then need to recompile the code. So that's for quadrature output. Okay, so then there is not this nice feature. So rather than having skip output, so what skip output does is it defines your output is print out every like n increment. But sometimes you don't like that. You just want, for example, if the simulation time is, let's say, 0.5, you want just to print out those information at 0.25 and 0.48 or at any specific time. Then the feature to use is set tabular output. This set tabular output and then define the times that you actually want to print out the output for yourself. What it does is it actually print out the quadrature output or the visualization output for you, depending if you set the flag true or not at these specific times. So this is very useful, but be careful. Even if all of the quadrature or visualization output flags are false, then it still will print out the stress-strain.txt file for you. And if you're interested to know what are the default quadrature output variables are, this is the list of those information you actually have here. All of them has been defined here. So that's for your output. There are two advanced features for the output. So let's say in your stress-strain.txt, there is a certain variable you want to print out as an average every increment. So then there is a feature that you can actually define a user-defined variable, and then that would be printed out for you using that feature, which I will try to at least point out tomorrow. And another feature is if you want to visualize any other variables than these four, what should you do? And I will cover that actually on the tomorrow's session. So that would be our output part or output sections. Is there any questions on the output sections I can cover now? Okay, there is no question in the chat box. So we'll continue with the boundary condition information. Okay. There are a different number of boundary conditions. And all of that can be, so if you have any question regarding any of these boundary conditions, all of them has been introduced in the documentation. There are a few new boundary condition that has been released on the last version of PRISMS-Plasticity, which are nodal boundary condition, tabular torsion boundary condition, and tabular Newman boundary conditions. So previously, we only could apply a deformation boundary condition, but now we can also apply tractions. So this is tabular Newman boundary condition. Now you can apply torsion, and also you can apply nodal boundary conditions. So it means that you can apply a specific deformation on a specific node in the specific direction. So these three has been added, and I try to explain at least where you can find the relevant information on those three on the documentation. But the boundary conditions that I will cover today is simple boundary condition, velocity gradient tensor, tabular boundary condition, and I will cover tomorrow the periodic boundary conditions thoroughly. So let's start with simple boundary condition. So the simple boundary condition is, as its name comes, it's simple. So the flag is set use simple boundary condition true. If actually there is no flag regarding that, it will be set as true. So you don't even have to put this flag. So there is a file for that, which is set boundary condition file name boundary condition info.txt that I will open it momentarily. And then you need to define how many header line you have, which is typically true, and how many boundary condition you're applying on that sample, which in this case it's 4. But what I mean by simple boundary condition is if you consider the sample as this cube, it has 6 faces. So for each face, you can define a boundary condition in a specific degree of freedom. So in total, you can define 18 degrees of freedom for this sample. So when I'm saying 4, it means that you just define 4 of these 18. And then if you open the file, it's something like this. So let me open the file for you to check it yourself. So if you open boundary conditions.info.txt, this is the exact file that you would have. This is for tension, which we are in the folder of external mesh. So let's go back to compression and boundary conditions. So this is the file you can see here. Header line, there are 2 header lines. And then there are 4 boundary condition, which means 4 lines. So each line has 3 columns. So the first column is face ID. So you define the boundary condition that you want to apply, what face ID you are trying to select. The face IDs are actually defined here. So it depends on X, Y, and Z. So there is face IDs on positive and negative side of each part. And then you can define. For example, in this case, the face 1 is here with normal in the X direction to that plane and on the negative side. So this is face number 1. The second column, it defines the degree of freedom, direction that you're applying boundary conditions. So it could be 1, 2, or 3. It means along X, along Y, or along Z. That's when you define the degree of freedom. And the last column for simple boundary condition is the amount of total boundary condition you're applying. For example, let's explain what this file tried to apply to this sample. The first line is face ID number 1, which is this face ID, along x-axis, which is 1, will be fixed during the simulation. So this face will be fixed along x, and let me try to write it down here. So this is along x. And then you have the same face ID along y is also fixed. So along y, consider this y. I know it's hard to differentiate it between z and y, but I'm trying my best. And then the same face along z is also fixed. So this is definitely not z, but consider it z. So this is fixed along all 3 directions. So you basically clamp this face. And then the last line, which is the 4th line, it says face 2, which is this face. You're applying along x direction compression. So you're actually compressing it towards this direction. So this is uniaxial compression. And the amount of deformation you define is minus 0.05. That sample length is 1, so that's 5% uniaxial compression. So this is how we define simple boundary condition. So let's go back to the next boundary condition, which is velocity gradient tensor. So with velocity gradient tensor, you can actually define the deformation gradient. So for example, sometimes rather than having displacement as an input, you have deformation gradient for an RV or representative volume elements. If you want to apply that to sample, you would need to set use simple boundary condition to false, and then set use velocity gradient boundary condition to true. And then there is a 3x3 matrix, which is that 9 components of velocity gradient. And velocity gradients will define that deformation gradients per time increment for you. The next boundary condition is tabular. So tabular, it's like, let's say you want to apply cyclic loading, not uniac, not monotonic loading, or a type of displacement with changing in the load path. Then you cannot use the simple boundary condition. Then what you need to do is you should actually define set use simple boundary condition to false, and then set use tabular boundary condition to true. And then you need to define a set boundary condition info table.txt. This file, let me open one for you to just explain it here. So if you go back one folder, there should be a tabular cyclic. If you open this, this is the type of file you would see. There is no header line. The first 2 columns is similar to simple boundary condition. So that defines the face ID, and that defines the degrees of freedom you want to apply. But the following columns are the amount of deformation for that face ID at that degree of freedom at different time steps. So in this case, you would have 1, 2, 3, 4, 5 time steps. And then if you check this, set number of time data for tabular boundary condition equal to 5. That's the number of time step you would have. And this is the file that I just showed you. So the first 2 columns I've already explained. So you can see there is a line, set tabular timetable 0, 5, 15, 25, 30. This is the 5 times that you have, 5 times that you would define. So you can see for each of those times, there is a value for each face ID and degree of freedom. So basically, what this boundary condition define is face ID number 1, face ID, let me try to go back to this cube. So I'm gonna go back and forth between this and the other one. So this says face ID number 1 along x-axis is gonna be clamped all the way. So this will be so no matter what time you're watching, this will be fixed. And then if you go back to this, then along face ID number 3, you would fix along y-axis again all the way to the simulation. So this is the case when you want to apply what we call symmetry boundary condition. So it's like modeling a symmetric boundary condition, and like if you try to model this, imagine in 2D, and the loading is symmetric, you can actually model 1/4 of it and put roller here. Now, if it's 3D, this is what we are trying to model. So we put roller here. Let's put roller. And then for face number 3, which is this one on the negative side of Let me clear this. So roller here along x-axis, and roller here along y-axis for this phase. And then on the phase 5, roller along z-axis. This is what we call symmetry boundary condition. And then you're applying uniaxial, not uniaxial, you're actually applying loading along phase 3 along z. So it's kind of uniaxial along z-axis, and it's going back and forth between -5% if you have a length scale of 1 to 5%. So this is the displacement actually you're applying. So this, it start with 0 and then go to -0.5 and then go all the way to 0.5 and then go back and forth. So the last part is loading along this, along z-axis on the face. And this loading, the sign is changed during the, as I show here. So this is how you apply tabular boundary conditions, basically. Okay, so let me clear all of this, close this. So that's how we apply tabular boundary condition. So the next line in the, let's go back to the input file we have in the terminal. So we define, in this case, we are applying uniaxial compression. And then the next part is you define the time step, total time, linear solver maximum number of iterations, relative linear solver tolerance, and maximum number of nonlinear iterations. So the first one is number of increments, time increments. So there is a rule of thumb that if you want to apply any kind of strain, the strain increment should be 0.0001 in each step. And that's a very good starting point. And if that simulation diverge and time step is too large, then you need to make it half until you reach convergency. Or on the other hand, if it's too small, then you can double it and make it larger to finish the simulation faster. So the first step for you in any material system is finding this strain increment for yourself. And then you define the total time of simulation. But the next two lines are maximum linear iterations and solver tolerance. So what it does is, because in real CPFE or real finite element simulations, the size of stiffness matrix is really large, we don't use direct solvers. We're using iterative solvers. And for that, if you know the famous equation of KU equal to F for finite element, you need to eventually find U equal to K minus 1, which is finding the inverse of K. And this process is doing iteratively here. So the number of iterations, maximum number of iterations for you to find this, the solution to this equation, and the residual that you need to have to reach for the solver to stop further incrementing or iterating will be defined here. So for your material system, you need to find that these numbers for a material system with the lengths of 1 and the properties very conservative, but I typically use more conservative values here to make sure my solution is converged rather than divergency during solution. So it's better to use more conservative values for here, but this is two other values that you need to define. Okay. So, okay. Oh, there is a line here that it has been missed, which is, so the maximum nonlinear iterations is in a find element, in a nonlinear find element. What you would have is one part that I already mentioned is KU equal to F. Solving this is a linear solution part, which is done by the FE solver itself. But if you are doing nonlinear material, or in this case, crystal plasticity is finite deformation plasticity, you cannot just solve each load displacement increment. So your curve is like this. It's different from a linear material, which your load curve is like this, and you can basically do the whole simulation in one step. What you need to do is you need to define some sub increment for each loading step, and then solving this by famous Newton-Raphson like this. So it requires certain number of iterations or for each increment of these load steps. This defines the number of iterations, nonlinear or Newton-Raphson iterations for each load step. Since our consistent tangent modulus is very accurate, in the most of the cases, using number 4 would be enough. It's actually a little bit more conservative. So you should definitely reach the convergency by using 4 Newton-Raphson iterations. So if you have a very complex nonlinear problem like contact, that number could goes up. So you need to be careful about that. So if you have very complex plasticity added to crystal plasticity, or complex nonlinear problems added to crystal plasticity, then you might need to increase that. But for a regular crystal plasticity simulation, this 4 would be enough. So the next part is you're reaching the elasticity parameters or mechanical basically constitutive model properties. So as you can see here, okay. So before I went to the constitutive model part, I will first explain the macrostructure, and then I will come back to these material properties, because we want to follow this PDF, so I don't want to confuse you. So if you go down all the way here, this is input macrostructure section. Basically, this is like the last part. So you remember in the grain ID.txt, I told you 2 variables which are important, 2 inputs. One of them was the number of header lines and the number of voxels in each direction. So you have 32 by 32 by 32, which means this is the number of voxels in X, Y, and Z. And this is the number of header lines for, and you need the name of the grain ID file you have. So grain ID.txt. So if you go, for example, open this grain ID.txt within compression folder. So let's go back to compression folder. And you open grain ID.txt, you would see you only have 5 header line. And then you would start this 32. But this 32 by 32 by 32 is NX, NY, and NZ. So as I mentioned, the format of this 2D array is, this is the number along Z-axis. So if you count this, it would be 32. And the number of rows would be NX times NY. So in this case, if you go all the way down, you would have here you would have 1029, which 4 or 5 of them are header lines. So it would be 1024. And if you multiply 32 by 32, it's 1024. So that's the number of rows you would have. So that's basically the grain ID.txt. So we have a question here. Can you please explain this again? Maximum number of linear iteration equal to 4. Okay, so the next question. So first, let me answer this 4. So imagine, let me open actually a new. Okay. Imagine you have a, oh, that was bad. I'm trying to, okay, this is much better. Let's say you have a nonlinear stress strain curve. And so whenever you are modeling nonlinear response, you cannot just solve it all the way in one step. You need to define the load steps. So let's say in this specific case, we have a load step of half. So this is the first load step. This is the second load step, which is unreal because typically it's way more than this. So then to reach from this point to this point, typically you cannot solve it in one iteration. So there are Newton-Raphson iteration, which basically what Newton-Raphson iteration does is you have an initial guess, and then you define the residuals based on this initial guess. So from this initial guess, you would define stress and strain. And from this, you would define residual. If the residual is 0, it means that you're done. You found the solution. But typically for nonlinear problems, this is not happening. So in the next iteration, so that would be your iteration number 1. In iteration number 2, what would you do is you define this delta U. Okay. You define this delta U. Why it's doing like this? Okay. Let me do one more time. Equal to, which is captured from this residual, which is actually, it's easy. It's equal to K inverse I times this Ri. And then this delta Ui will be modifying this initial guess. That would be your second iteration. Now, from this, you would calculate another residual. So the question is, if you are using a really good algorithmic tangent modulus, then your convergency would be really quick. And then the number of these trials would be very small. So in PRISMS-Plasticity, we calculate very accurate stiffness matrix. So the number of these trials to reach the convergency, it's very small. So if you try this again and again, that would be your convergency. So this number here, this is what you know as the number of nonlinear iterations. So that's what I call number of nonlinear iterations for a Newton-Raphson for PRISMS-Plasticity equal to 4. So I think that has been clarified. So the next question was, as you mentioned, contact. So no, you cannot use that coupled with other commercial softwares. But for example, a very important application of contact is indentation. So we are almost done with the release of indentation module for PRISMS-Plasticity. So we actually implement our own contact. But besides that, if you're interested in more complex contact problem, you should be careful for 2 reasons. A, from the experience that I got in implementation of indentation module, the crystal plasticity itself is very nonlinear. And the contact itself is also nonlinear. So mixing contact with crystal plasticity, it's a very complex daemon that it would be really hard for you to converge it. So even the simple task of indentation would sometimes be really hard to convert. So even if, like from my experience from Abacus, even if you use simple continuum model, sometimes after certain amount of indentation depth, you would get convergence issues because of the element reduction or element skewity. So be careful when you're trying to mix contact with crystal plasticity. These are fancy words, but this is sometimes it becomes really challenging. But answer to your question, indentation module will be released, but you cannot mix this with commercial softwares. So let me go back to the PDF. So there is an advanced feature that I will briefly note tomorrow is element deletion. So imagine, I'll just give you an what the capability is, and then you can, I'll cover it in more detail tomorrow. Imagine you have a sample and you want to make a notch here. What PRISMS-Plasticity is capable of now is you can define, so initially, let's say Prisms, Dream 3D will give you an intact macrostructure. Then what you can do is you can process this file with like a MATLAB and define a notch here by assigning the grain ID of 0 to that notch. And then there is a feature here, set grain ID deletion. And if you activate that, it will, the final macrostructure would be actually like this. So it will automatically delete that notch for you within the software. So that's one important feature that I will cover tomorrow. Try to at least go over what would be the required lines for that. So the final parts for the input file will be the material, the constitutive model itself. So we have implemented two different constitutive models. Today I will cover rate independent, but tomorrow I will cover rate dependent model. So for rate independent model, for each slip system, you have a yield surface, so which is defined here. And the crystal plasticity model, it has multiplicative decomposition. And the key idea of crystal plasticity is relating plastic velocity gradient in intermediate deformation configuration to the plastic slip activity on each slip system. So that's the key idea of this constitutive model. And then you would have evolution of slip resistance, and this is the hardening model that we have. So this is just to give you an idea about what parameters you need to define. So the parameters you need to define is, you need to define this H naught for each slip system, which is initial hardening, the saturation hardening, the exponent value, this latent hardening, and initial slip resistance. So basically what you have is the total slip resistance would be initial resistance plus the hardening that you would get. This hardening will come from this equation. So this is another parameter you need to define. And you have elastic parts, so you need to define the elastic modulus for that sample. And what else? No, that's it. For rate independent model, these are all the parameters you need to define. So let's go to the next page. So the first part that you can actually see here is the, let's go back up. It's the elastic modulus 6 by 6 in a Voight notation with the unit of megapascal. So for FCC, HCP, BCC, for different materials, that could be different, but you can get these values from literature anytime. So that's not, that's typically not an issue. The next part is defining the number of slip systems. So how many slip systems your system have? This is an FCC sample, so it has 12 slip systems. The next part is latent hardening ratio. So latent hardening ratio, it defines plastic slip system hardened their coplanar system different than some slip system on different planes. This differentiation will be captured by this latent hardening ratio.txt. But initially, we just had a simple parameters, latent hardening parameters, which is working for FCC system. What it does is, if you actually have a system of hardening parameters, for example, let's say you have a basal, but you have a FCC system. So your hardening would be 12 by 12 matrix. And on the coplanar system, this latent hardening value would be 1. So for each 3 slip direction, which is in the same plane, they are coplanar. But for not coplanar systems, you have a multiplication number here, Q, which will be your latent hardening parameters, and that would be the rest of the parameters here. Same here. So simply for FCC, if you define this Q, you can define this 12 by 12. So the next component here would be 1, 1, 1. So it's a 3 by 3 identity matrix, not identity, 3 by 3 ones matrix. And here you have Q, 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 sorry for the bad handwriting, Q, and all the way. I think you understand what I'm trying to say. So what if you have a material system which have different latent hardening for different systems? Like you have HCP, and you have basal, prismatic, pyramidal, and you don't have unified Q for all the system. Then that's the complexity. So we decided, rather defining just one simple Q, we need to define this matrix as a whole. So we have a file here, which is latent hardening ratio.txt, which actually defined this 12 by 12 matrix. So if you open this latent hardening, you see this is, so 1.4 is that Q that I mentioned. So in the case of FCC, all of that is 1.4. But you might end up with, in the HCP sample, with coefficient which is different than 1.4 for different systems, or different numbers for different systems. So you need to define. So in this case, you have a 12 by 12 matrix. For coplanar system, this is 1. For not coplanar system, this is Q, which is 1.4. So this is a file that you need to define for your latent hardening ratios. Okay, so let's go back to the input file. After that, since you have 12 slip system, you need to define, as I mentioned, 12 initial slip system. Let me view, zoom out. Okay, that's better. So 12 initial system, 12 initial slip resistance, 12 initial hardening, 12 power law, and 12 saturation stress. So these are the parameters that I actually define here. Initial hardening, saturation, exponent, and I mentioned initial slip resistance without any hardening. For rate independent, also you need to define the crystallography of those slip systems. So it would be slip direction and slip normals. So you should have 12 slip direction and 12 slip normal, which in this case, slip direction would be 110, which is, you need to have a normalized slip direction. So it's 1 over square root of 2, 1 over square root of 2 O direction, which is 12 of those. And you would also have sleep normal, which should be 1, 1, 1, which is 1, 1, 1 sleep normal, which is 1 over square root of 3 if you normalize that. So that would be your sleep direction and sleep normal. So with that, that's the most simple file that you would have. These three, you don't need to worry about them right now. This is more on the numerical methods. We are solving the crystal plasticity model. So before I went, so after this, we can now, I covered this. So we can start the simulation. But before that, let's see what questions do we have. Please, where is the alpha and beta defined? What do you mean by alpha and beta? Oh, alpha and beta, you mean in the here? Okay. So beta is actually, it's for each sleep system, and alpha is, oh, okay, I see what you mean. So you remember that 12 by 12 sleep system? That's a very bad place to draw. Let's say this is 12 by 12. This is actually alpha beta. So this matrix, alpha, for example, let's say alpha is 1, beta is 1. This is this component. Let's say alpha is 1, beta is 2. This is this component. So that's the latent hardening matrix that I just mentioned. It's 1 Q or 1.4 in that case. So I think that answered your question. If not, let me know. So different crystal structures could be implemented through manipulating sleep normals. That's correct. And on top of that, you need to modify the latent hardening ratios, and you need to define elastic modulus. So basically all the only part you need to modify in the input file would be the material part. So it would be, let me close this. It would be this section. From here to here. That's the only part. So tomorrow I will cover the rate dependent model as well. And then that would be a slightly different look on the input file, but this is the most simplest one. So now let's go to do one simulation. So if you go to your PDFs, the simulations that we would like to do is here. Plasticity applications, crystal plasticity, FCC random orientation block. So if you open your here, let me start from a new terminal for you. So if you open a terminal and then you go to tools, so CD tools, let me zoom in a little bit. And then plasticity. So the rest of the address would be similar to what you have here. So plasticity applications, crystal plasticity, FCC random orientation block. So you need to just add tools previous to plasticity. So CD tools, plasticity, application, crystal plasticity, FCC. What's the question? Is it possible to manipulate the phenomenological? Yes, there is a backstress for both rate independent and rate dependent model already implemented. So you can just, I will cover how it look like for rate dependent. For rate independent, you can see the documentation. I'll cover the rate dependent for backstress tomorrow, actually. So FCC, what was the name of the folder? I forget myself. FCC random orientation block. So let's say FCC underline random orientation block. So this is the folder that I'm going to run. Just to show you how would the input look like, I will show you the folder here. So I will start from the home. So I will open tools. So you can just click on this and then click on tools, plasticity, applications, crystal plasticity, FCC, FCC random orientation block. This is the files you would have in that. So let's check the boundary condition first. So boundary condition, it says 1, 3, and 5. So this is symmetry boundary condition that I mentioned within the tabular. So what it does is it fixes like a roller for symmetry boundary condition and then apply compression in the Z direction. And since the sample size is 1 in this example, it's 5% compression for that sample. And if you go back here and open the main PRM.PRM, so this has sample 1, 1, 1, so unit length. The discretization is 5, 8, 10. So in this example, the refine factor is 2. We want to make it 0. If you don't make this set refine factor 0, your simulation will take longer. So if you go to your PDF, I've already mentioned that, nope, but do that. So make your refine factor 0. I think it's 0. I have mistakenly changed it to before the training started. So I think it starts with 0 for your case. Am I right? Someone please confirm if it's 0 or 2. Yep, it's 0. Okay, that's good. Stick to 0. So now what you're modeling is 5 by 8 by 10 discretization. So this specific example, this is not based upon a real macrostructure. This is what they call each element is a grain ID. So this is like a cubic macrostructure, which each element is, this is one of the initial macrostructure people used to do when they did CPFE simulation. And so the set write output, you need to make it true. So on PDF, I said set write output true. And then set skip output equal to 25. So every 25 increments, it will output for you the results. So that's 25, correct? And then make everything true besides the twin fraction. Okay? So that's the only change you need to do. And then you can save it. This is the easy way if you don't have any Linux background. But you also can open the PRM.PRM here and then modify those information here as well, which is basically the same. So it doesn't matter how would you change it. On clusters, you don't have this kind of nice editor, so you have to stick with some kind of editors in the terminal. After that, you can just, so boundary condition, I've already mentioned it, and you have the time increments. So now you can start the simulation. And after 50 increments, you can kill it. So let's say MPI run -n. So the command is here if you are interested. So MPI run -n to ... main PRM.PRM. So this is the command you need to type in. So 2 processors, main. So after 50 increments, you can kill it. Basically, it will output for you 2 increments because you set the skip output equal to 25. So let's give it like a minute or so. if you have a more power, like if you have already set more number of processors, you could have actually used 4 or even larger. I just want to stick to basics that we all have at least. So we finish about the same time. So let's check the terminal. 12 of them has been finished. Meanwhile, if you have any questions, that's a good time until our simulation is done. I can answer those questions. So if you delete the grain ID, how can you visualize it? Power view. Yep. After you finish the grain ID, after you finish the simulation or some way in the simulation, like what we are doing right now, if you put the set skip for every increment, you actually get to see the visualization at those time steps, and you could see that the element has been deleted already. Is Prisms compatible? So the only problem with the installation is not with Prisms, it's with DIL2. So Prisms would be pretty straightforward. So the packages for Prisms that you need to install are some kind of LAPACK or BLAST that some of the clusters, they have already have MKL, which is doing the same, and PETC and pForest. Those three, if you compile them, then you need to compile DIL2 with those. So I would say most of the problem with cluster installation is coming from DIL2, and the best way to handle that is to ask questions about that from the DIL2 group. But the best way to figure out what actually the problem is, when you are doing make release, do it make debug. So just give you an idea, last week I was doing an installation on our cluster, new cluster, but everything looks good. But when I was doing the simulation, I did get the error after the first increment. When I did make debug, it showed me at the line with LAPACK was used, something is wrong. Then I figured out, oh, the LAPACK installation is not working. So, and then I went check, when you do CMake with Prisms or DIL2, it showed which packages have been successfully installed. So that gives you the idea of if you have successfully installed pForest, PETC, and LAPACK. Those installed successfully, honestly, nothing should have happened, but sometimes some people would face some installation issues with the newer version of DIL2. So my next suggestion is try DIL2. The current version is 9.4. I successfully installed that with PRISMS-Plasticity on both cluster and local machine last week. But you can also try DIL2 9.2, which is more stable version. So, but definitely use make debug to see where the error is coming from, and then try to go from there. So can this function be implemented to other software solver? I don't know. I've never tried it, so I think it should be, but I don't have much expertise with implementation on other solvers, so I don't have any comments on that. So let's see. Okay. I have one installation for my cluster. I can share with anyone interested. They can send an email. But each new cluster, I had to challenge myself. It's not an easy thing to do. 2-3 days, you definitely need to get help of people from your HPC. But the bottom line is you need to install, compile LAPACK or BLAST or kind of MKL, which they have already compiled as a module. And you need to have PETC and pForest and DIL2 along those packages for PRISMS-Plasticity. I have an installation, I can share it with you, but even for our clusters, when we change it, it doesn't work for another cluster. So it's not easy, honestly. So, but anyone interested, I can share that one with them, but it's not what's probably working for their. So let me kill the simulation. That's more than 50. So let's go back to the folder, and now you can see there is a result folder here. So if you open this result folder, there is a stress-strain.txt, which is the homogenized response. I will open it momentarily. But you also have solution PVTU and projected field PVTU. What's the difference? The nodal displacement is always the solution of this KU equal to F. So all the nodal displacement will be saved in solution some number PVTU, which this number is actually the increment number that it has been printed out. But some information, like let's say one meter stress, strain, some state variables, if this is an element, they are all calculated at quadrature points. But the visualization tools like ParaView, they need information at the nodal points of the mesh. So what we did is we kind of inverse solving this KU equal to F with a stiffness matrix we call projection stiffness matrix to extrapolate these values or state variables from quadrature points to nodal values. So that's the reason we print out those values as projected fields, which includes 1 meter stress strain, grain IDs. So grain IDs is on both projected and solution. So this is the difference between solution and projected. Only nodal values and grain IDs are provided here. And since we already outputted only 2 outputs, because a skip output was 25 and we simulated like 60 something, you can see that there is a PVTU 0024 and PVTU 0049, which is 24 because it's start from 0. So it's 0 to 24, one output, 25 to 49, another output. So you have outputted the results for 2 time steps. So that's the name of the files. Let me clear all this mess. So now let's go and open something that we have here. We call it LibreOffice. If you have Windows, you can use Excel for this. So let's see, what do we have? Open this LibreOffice. So for LibreOffice, you can menu, open menu, and then Office and LibreOffice Calc. So now you need to open that stress-strain.txt that you have. So I start from home in case it start from home for you. So from home, you go to Tools, Plasticity, Applications, Crystal Plasticity, FCC, FCC Random Orientation Block, Results, and then a stress-strain.txt. The same address as you have the runs. If you double click on the stress strain and then click on OK, you will see how does the stress strain look like. The 6 component of strain averaged over the sample, the 6 component of stress, these 2 are related to twinning and a sleep total on the last column. So we know that we apply the compression along ZZ axis and it's normal compression. So if you actually plot EZZ versus TZZ and then select these 2 columns, so for selecting, you can just click on this C column and shift control and then click on this I column. That would selecting the whole column. And then set insert chart and then select XY and then say finish. And that would be your stress strain curve, and it's compression, so it's along minus strains and negative uniaxial stresses. So that's how you can actually plot the stress strain curve. That's one output you want to do. So another output would be if you go here, let me see, there is a question. Is this true or engineering strain? So this is a green strain tensor. And if you want to have true strain, engineering strain tensor, you know that each of this, so if I want to plot engineering strain, I would insert a column before, and then I know each of this is engineering strain for ZZ. And I know I'm applying 0.0005 minus for each increment. So, and then I will add this minus 0.00005. So this number, you can see it's very close to green strain tensor for small strains, but then it's going to deviate it from that eventually. And then I will double click on that. It will paste the formulation there. And then you can have also true strain, which I believe it would be ln, oh, sorry, 1 plus this. I don't know if this is working in Excel, but I'm not sure if this is working here. So let's try. Oh, no, it was working. And then double click here. So now you can have plotted versus true strain or engineering strain. Okay. Yes. Oh, I had set right output to true. So did you change also the number of increments there? So in your input file here, you need to also change this to 25. Did you do that as well? Or not? Because if you didn't change that, the number, I think the original number is 10,000. So you need to actually simulate 10,000 for that. So that's too much. You need to have it 25. So, okay, great. So now you can open the para view here. And then within the para view, you can say File, Open, and then go to Home, go to Tools. Where is Tools? It's here. And Plasticity, Applications, Crystal Plasticity, FCC, Random Orientation Block, Results, and you can open both solution PVTU and project PVTU. Fly. Okay, now let's start with solution PVTU. So you can do this. Let's start with project. Solution is actually better. Let's say U, and let's say surface with edges. So you have 5 by 8 by 10, and we want to simulate how much along Z-axis you actually display it. So we apply compression Z from this side. So you can see this blue line is negative 1.2 displacement along Z-axis, and this side you fixed it along Z-axis. But an interesting application would be you actually try to visualize the deformed sample. We didn't apply much deformation, but let's say filters, you can go, oh, sorry. Filters, let's see, data analysis, what was that? Common, yep. So if you go filters, common, there is a warp by vector. So if you click on this warp by vector, And because our deformation is small, you need to increase scaling factor to, let's say, 50, and then say apply. So this, you can actually go back and forth between the simulation steps. So this is the first simulated steps, and this is the second one. I think we have only two. So this is not the undeformed state. This is increment 25, and this is increment 50. So that's the compression. And another thing is you can actually plot the like equivalent stress, and you can march over the time, and then you can rescale that. So typically what I would do is I would go to the last step, rescale that, and then march back to see how it changed. So this is pretty much the basics of PowerView, but as I mentioned, there are a lot of advanced capabilities that I'll try to cover tomorrow. Hopefully to how do you want, if you want to add anything, like now you have equivalent stress, strain, mesh ID. What if you want to visualize sigma 1,1? What should you do? Or now you have everything here, but what if you want to have another component here? What should you do? So these stuff I will cover tomorrow. But before that, if you go to the PDF, there are some explanation. It's here for what I just explained. Here again, it's more details of what I just went over on the PDF. And this is what I did. This is just with the Excel. So this is playing with the input file for you till the next session. This is some small exercise for you. So use a more refined mesh. It says set refine factor to 2. Sometimes the memory of some virtual machines are not good. And if you use 2, it will gives you out of memory. But if it works with 2, that's fine. It should be the same. It's just higher resolution for mesh. Output quadrature outputs and see how it look like. So we didn't talk about quadrature outputs here. So it would be nice for you to see what it does. There is some instruction for that. And then applying a cyclic loading using tabular boundary condition for the same application, that I will go over that next session. So it would be nice for you to cover that as well as an exercise for yourself for tomorrow's session.